To process light into vision, the human eye relies on a dominant optical engine, the cornea. This transparent dome at the front of the eye provides approximately 75 to 80% of the system's total refractive power. In a healthy eye focused at infinity, the total refractive power sits between 60 and 65 diopters. The cornea alone accounts for 43 to 48 of those diopters. Generating this much power requires a specific refractive index. The cornea maintains an index of 1.37 against the surrounding air's index of 1.00. To achieve this transmittance without distortion, the tissue must be perfectly transparent and completely avascular. This creates a strict biological constraint. The cornea contains no blood vessels, yet it must function as a living, metabolically active tissue while providing a tough, fibrous exoskeleton for the globe. Achieving this clarity relies on a highly specific microscopic architecture and relentless, energy-consuming physiological maintenance. Looking at the macroscopic geometry required for proper image formation, we find a structural asymmetry. When viewed from the front, the cornea appears elliptical. It measures an average of 11.7 millimeters horizontally, but only 10.6 millimeters vertically. This occurs because the opaque sclera and conjunctiva slightly overlap the superior and inferior edges of the cornea at the limbus. Viewed from inside the eye, the posterior measurement disparity disappears. The internal boundary is a perfect 11.7 millimeter circle. Optical power relies heavily on surface curvature. The anterior surface maintains an average radius of exactly 7.8 millimeters. The posterior surface curves steeply, possessing a 6.5 millimeter radius. These exact geometric parameters dictate where light focuses on the retina. Holding this precise shape requires us to look past the macro measurements and examine the microscopic layers that build the structure. This high magnification light micrograph displays the full histological cross-section of the tissue. While historically divided into 5 layers, modern histology confirms the cornea is composed of 6. Layer 1 is the non-keratinized stratified squamous epithelium. It's roughly 50 micrometers thick, built from 5 to 7 tightly packed cellular layers, including basal, wing, and surface cells. Interfacing directly with the precorneal tear film, it creates a perfectly smooth optical surface renewed with every blink. The epithelium is also heavily innervated. It receives its nerve supply from the ophthalmic branch of the trigeminal nerve, making it one of the most sensitive tissues in the human body. Because these nerve fibers pass directly through the optical zone, they shed their myelin sheaths after penetrating the limbus. By the time they reach the central cornea, they are unmyelinated, hair-like strands that will not scatter incoming light. Immediately beneath the epithelium sits layer 2, Bowman's layer. This thin, acellular sheet protects the underlying stroma from external injury. These first 2 layers act as a defensive barrier, providing rapid cellular regeneration and extreme physical sensitivity to protect the eye without obstructing vision. Moving deeper, this cross-sectional diagram highlights layer 3, the stroma. It is the structural core of the cornea, making up approximately 90% of the total tissue thickness. The stroma is constructed from 200 to 250 transparent collagen lamellae, which are suspended within an extracellular matrix. These lamellae are arranged with exacting precision. Each layer of collagen fibrils is laid down at strict right angles to the adjacent layers, never interweaving. This specific architecture dictates the biophysics of corneal clarity.
The fibrils are held at incredibly uniform distances from one another, a spacing that prevents the scattering of light waves. The opaque white sclera surrounding the cornea is built from the exact same collagen fibrils. However, in the sclera, those fibers are arranged haphazardly, resulting in complete opacity. The stroma achieves its dual purpose, immense tensile strength and flawless optical clarity, through the uniform geometry of its internal matrix. Below the stroma, this 3-dimensional diagram isolates the deep posterior boundary layers of the cornea. The 4th layer is a recent histological discovery, known as Dua's layer, a distinct and highly resilient pre-descimate structural barrier. Directly beneath it lies the 5th layer, Descemet's membrane, which serves as the basement membrane for the tissue's final boundary. The 6th and innermost layer is the endothelium. It is a strictly single layer of hexagonal cells bordering the aqueous humor. The endothelium is tasked with solving the stroma's greatest vulnerability. By its chemical nature, the stromal matrix constantly attempts to absorb fluid, swell, and become opaque. To counteract this, the endothelium employs an active pump leak mechanism to maintain a perpetual state of relative dehydration. Each individual endothelial cell contains approximately 3 million ion pumps located in its lateral membranes. These pumps push water and ions against a concentration gradient to drive fluid out of the stroma. Sustaining this state of perpetual dehydration requires a massive, constant, and relentless energy expenditure from every single endothelial cell. This active pumping and rapid cellular regeneration demand a constant supply of energy. Without a vascular network to deliver blood, the cornea relies on alternate metabolic supply lines. For its oxygen requirements, the tissue relies heavily on the external atmosphere. Oxygen gas dissolves directly into the precorneal tear foam and diffuses down into the epithelial cells. Nutritional components, such as glucose, amino acids, and essential vitamins, arrive from the opposite direction, diffusing upward from the aqueous humor. These nutrients pass into the tissue because the junctions between the endothelial cells are intentionally leaky. This structural gap allows necessary diffusion to occur, but it is precisely this passive leak that the active cellular pumps must fight against. The cornea operates on the fragile metabolic supply chain, suspended perfectly between the external atmosphere and the internal fluids of the eye. This delicate physiological balance is stress-tested every single day through a standard human behavior, closing the eyelids to sleep. When the eyelids close, the primary supply of atmospheric oxygen is cut off. Relying on the limited oxygen provided by limbal papillaries and the aqueous humor forces the cornea into a mild state of hypoxia. Because oxygen is required for cellular respiration, the millions of endothelial pumps are starved of the energy they need to function efficiently, and their output slows. As a physical consequence, the constant inward leak of fluid outpaces the outward pumping action. Water builds up within the collagen matrix, causing the entire stroma to swell and increase in thickness over the course of the night. This physiological edema reverses within a few hours of waking as atmospheric oxygen resumes fueling the pumps. The architecture of the cornea represents a strict biological compromise. By sacrificing the stability of a normal vascular blood supply, it achieves perfect optical curvature and flawless transparency, functioning as a relentless engine.